So, good afternoon, class. For this afternoon, I am your instructor, Crystalmi E. Bustamante, Basic 3 Mathematics. This is my first report for Abstract Algebra 2. So, my report is tackled about prime ideal and maximal ideal. A prime ideal A of a commutative ring R is a proper ideal of R such that A, B is an element of R and AB is an element of A, imply A is an element of A or B is an element of A. A maximal ideal of a commutative ring R is a proper ideal of R such that whenever B, this capital B, is an ideal of R and A is not equal to B and B does not equal to R, then B subset of A or B subset of R. So, example, let n be an integer greater than 1. Then, in the ring of integers, the ideal nz is prime if and only if this n is prime, like 2, prime number, like number 2 greater than 1. N is an integer that greater than 1 since it is prime number, so example of a prime number is number 2. So let n be a prime number. Nz is prime ideal. Nz is a set of z that is verified. Nz is a deal of z. Verify. Let A is an element of z and B is an element of z. And AB is an element of an integer of z. AB equal to nx. F dot sx is an element of z. Then n is divided by nx equal to AB. Since n is a prime, therefore n is divided by A or n is divided by B. Then A equal to NP or B equal to NQ. F dot S P Q is an element of Z. A is an element of NZ or B is an element of NZ. Then NZ is a prime ideal. To converse, let NZ be any prime ideal of Z. To show n is prime number, let if possible n is not prime. Let n equal to n sub 1, n sub 2, where 1 is greater 1 is less than n sub 1. N sub 2 is less than 2 n, which n is an integer that is greater than 1. Since nz is prime, n sub 1 is an element of nz or n sub 2 is an element of nz. This is a contradiction as n sub 1 is less than to n and n sub 2 is less than to n. Therefore, n is at least positive VE, Z, and Z. For example, second example, x squared plus 1 is maximal ideal of R of x. This is the solution. Let m equal to x squared plus 1 equal to x squared plus 1 f of x. F of x is an element of R of x. Since 1 is an element of R of x, but 1 is not an element of m, therefore m is not a subset of Rx. Let A be any ideal. If A equal to m, then we are done. If A does not equal to m, then m is not a subset of A and A is a subset of Rx. Now we will show that A equal to R of x. Since m is not a subset, now we will show that A equal to R of x. Since m is not a subset of A, therefore f of x is not an element of S dot T f of x, and f of x is not an element of m. By division algorithm, f of x equal to r squared plus 1 and q of x plus r of x, where r of x is equal to ax plus b. If r of x equal to 0, then f of x are equal to r squared plus 1 q of x, an element of m, a. Contradiction. Therefore, a does not equal to 0 or b does not equal to 0. Then ax plus b equal to r of x equal to f of x minus r squared plus 1 q of x, an element of a. Then a squared multiplied by x squared minus b squared equal to ax minus b multiplied by ax plus b is an element of a. So 0 does not equal to a sub 2 plus b sub 2 equal to a sub 2 multiplied by x sub 2 plus 1 minus a sub 2 a squared x squared minus b squared is an element of a and is equal to c and equal to a squared plus b squared does not equal to 0 belong to a. Since c is non-zero real number, therefore c is the power c to the power of -1 exists in R subset of R of x. 1 equal to c dot c to the power of -1 is an element of a. Let g of x is an element of R of x. G of x equal to 1 multiplied by g of x is an element of a. Then a is equal to R of x. Then m is maximal. So for theorem 14.3, let R be a commutative ring with unity and let A be an ideal of R. Then R is divided by A is an integral domain if and only if A is prime. So this A is a prime. For theorem 14.3, let R over all over A be an I dot A dot. To show A is a prime ideal, let AB is an element A. AB plus A equal to A. A plus capital A multiplied by B plus capital A equal to 0 of R over A, all over A. A plus capital A equal to capital A or plus A equal to A. Therefore, R all over A is I dot D. A is an element of A or B is an element of A. Therefore, then A is a prime ideal. To converse, let A be a prime ideal of R. To show R all over A is an I dot D since R is commutative ring with unity. Since R all over A is commutative ring with unity, so unity equal to 1 plus A. Let A plus A multiplied by B plus A equal to 0 of R all over A equal to A. AB plus A equal to A. AB is an element of A or B is an element of A equal to A. Then R all over A is an integral domain. Theorem 14.4. Let R be a commutative ring with unity and let A be an ideal of R. Then R is divided by A is a field if and only if A is maximal. Let R all over A be a field. To show A is a maximal ideal of R. Let B, this B capital letter B be only ideal of R. S dot T dot A is not a subset of B and B is a subset of R. Since A is not a subset of B, therefore B is an element of capital B. S dot T dot B is not an element of A. Since B is not an element of A, then B plus A is not an does not equal to A. As R all over A is filled, every non-zero element is unit equal to B plus 1 to the power of negative 1 exists in R all over A. Then B plus capital A multiplied by C plus capital A equal to 1 plus capital A if that is C plus capital A is an element of R all over A. Or BC plus A is 1 plus A or 1 minus BC is an element of A. 1 equal to 1 minus BC plus BC is an element of B. Then B equal to R. Then A is maximal ideal of R. Converse, let A be a maximal ideal of R. To show R all over A is a field. Since R is a commutative ring with unity 1, therefore R R all over A is a commutative ring with unity plus 1 plus A. For showing R all over A is a field, it is enough to show every non-zero element has an inverse in R all over A. Let x plus a is an element of R all over A. X plus a does not equal to A. In other words, x is not an element of A. To define B, Rx plus A, R is an element of R, capital R, and A is an element of capital A. Let P equal to R sub 1 x plus A sub 1 is an element of B. Then Q is equal to R sub 2 multiplied by x plus A sub 1 is an element of B. Then R is an element of capital R. P minus Q equal to R sub 1 minus R sub 2 x multiplied by A sub 1 minus A sub 2. And then PR equal to R sub 1x plus A sub 1R equal to R sub 1 R multiplied by x plus A sub 1 R. Therefore, R is commutative. RP equal to PR is an element of B. Therefore, R is commutative. Let T is an element of A. Since T is equal to 0x plus T is an element of B, then A is a subset of B. Since x is not an element of A and x is equal to 1, dot x plus 0 is an element of B, then A is not a subset of B. Then A is not a subset of B, and B is a subset of R, and A is maximal. Therefore, B equals to R. Then 1 is an element of R equal to B, then 1 equal to R sub 0 x plus A sub 0. F dot S R sub 0 is an element of R, A sub 0 is an element of A. A plus 1 equal to R sub 0 x plus A sub 0 plus A. R sub 0 x plus A sub 0 plus A equal to R sub 0 x plus capital A. Capital A then equal to R sub 0 plus A is multiplied by x equal to A. Then x plus A is to the power of negative 1 is equal to R sub 0 plus A is an element of R all over A. Then R all over A is a field. So that's all. Thank you. That's my report for this afternoon. Thank you so much for listening and watching.